Today we're going to talk a little bit about Kepler's third law. Yesterday we talked a little bit about Kepler's first law and second law. In the third law, we're going to kind of recreate some of Kepler's original observations. One of the things he did was he was interested in if there was a relationship between how far away the planet was from the sun and how much time it took it to go around. So he took some data and he was looking at basically the 5 planets we could see, right? So Mercury, Venus, Mars, Jupiter, and Saturn. You can see those with the naked eyes. And he plotted down here, he plotted the radius. And here he plotted what we call the period. Now, the question is, how do you measure the radius? In solar system context, one of the ways that we measure the radius is we measure it in terms of something called an AU. An AU is an astronomical unit. It's basically the average distance from the Earth to the Sun. It's about 93 million miles or so. As we talked about yesterday, the Earth actually goes around in an ellipse, and so it varies a little bit more than 93 million, a little bit less than 93 million, but the average is about 93 million for the Earth. Over here, the period, one of the things you can do is you can measure it in years, because we know that's 1 Earth year. It turns out that Mercury and Venus take less than a year to go around the Sun. Mars takes more. We're going to see that here. One of the things about this, the period, we use a capital T for period because it's a period of time. And this is radius down here. We're going to use a little, maybe we'll use a big R for radius. And so what Kepler thought, pretty astutely, is he said, oh, I bet if it's farther away, it's going to take more time. So as the radius increases, the time it takes to go around also increases. But the weird thing about that was that we think, oh, well, what if it's linear? If you're twice as far away, does it take you twice as long to go around? Or maybe it's quadratic. If you're twice as far away, it takes you 4 times as long to go around. But what ended up happening was he got a curve. But this curve, the exponent of this isn't 1, which would make it linear, and it's not 2, which would make it quadratic. It turns out that the equation he got for this is that the period is proportional to, now I know this is the Greek letter alpha, it has different meaning in different contexts, but here it means is proportional to the radius raised to the 1.5 power. Now, what on earth does that mean? Well, he was a little perplexed because there was nothing like this in nature before. But if we do a little work here with our brains, we can actually come up with a really interesting kind of understanding about this. Now, when we look at where all the planets are on here, you know, if we put the Earth, let's say the Earth is here. So the distance of the Earth is 1 AU, and it takes 1 year to go around. That's the Earth. Mercury and Venus would be over here. Mars, Jupiter, and Saturn would be over here, but everybody's somewhere on this line. So this is Saturn, Jupiter, Mars, Earth, Venus, and Mercury. So what does this mean? Well, it means that the farther out you are, the more time it takes to go around. But the 1.5 is a weird thing. But 1.5 is also a fraction. And if we write this in terms of a fraction, we can see that it's 3 halves. And if we know how fractional exponent works, this is actually a square root here, right? So this is r cubed and the square root. Now, I don't like fractions, so what are we going to do to both sides? In essence, we're going to square both sides. So if I square the left side, I end up with t squared is proportional to, and if I square this side, I end up with r cubed. Now, because we're using AU in years, this actually equates to a coefficient of 1, because if we put it in for 1, if the radius of the Earth is 1 AU and years is 1 year, 1 cubed is equal to 1 times 1 squared. And so this coefficient here is 1 if we're using these units. Now, if we use different units, this would be different, and that's totally a fine way to do this. But the thing that's important is what Kepler came up with, because he didn't use AUs in years, who knows what he used. What he ended up with was this idea that the t squared over r cubed ratio is equal to a constant for all planets that are going around the sun. This is a crazy idea because it doesn't matter where you are in the solar system, as long as you're going around the sun, the t squared over r cubed constant is a constant. Now you could also flip this over and be like, no, it's r cubed over t squared. This would also be a constant. These two wouldn't be the same, they would obviously be reciprocals because of this. But what this means for us is that if you know the radius of any planet in the solar system, you can figure out how long it's going to take it to go around. Or if you know how long it takes to go around, you can figure out how far away it is. Here's how this manifests. Here's how this manifests for us. According to the way we did this, we're going to use this equation here. So we know that t squared is equal to 1 over r cubed, but the 1 is not that important. Let's say we're going to find a new planet. Okay, our new planet is somewhere out there. I'm going to say, oh gosh, astronomers found a new planet. Okay, and what they realized was that this new planet is 10 times as far away from the Earth, or 10 times far away from the sun as the Earth is. If we know how far away it is, do we know how much time it's going to take to go around? Well, here's what we're going to say. I know that the t squared over r cubed ratio is constant. We're going to use a little k for constant for all planets in the solar system. Therefore, I could say t squared over r cubed for Earth, I'll put an e here for Earth, has to be equal to the t squared over r cubed for this new planet, which we'll call p for planet. And I'm telling you that r for the new planet is equal to 10 times r for Earth. Well, I'm going to take this and I'm going to substitute in here and see if we can't solve. So I end up with t squared Earth over r cubed Earth is equal to t squared for the new planet divided by 10r Earth. But here's the thing though, we have to cube it. And so, working with this a little farther, t squared Earth divided by r cubed Earth is equal to t squared for the new planet divided by 1,000 r Earth cubed. Now, these two things, obviously, somehow, they're going to magically disappear. I'm going to multiply both sides by 1,000. So I have 1,000 times t Earth squared is equal to t of the new planet squared. And then to solve for this, I got to take the square root of both sides. And I end up with that t for the new planet is equal to the square root of 1,000 times the t for Earth. And so we end up with this idea that you can solve for the period of the new planet or in relationship to the period of Earth if you can use this equation right here. So the idea that t squared over r cubed is a constant, or r cubed over t squared is a constant, this is Kepler's third law. and this is an application of it. And we're going to see how this does or does not gel with Newton's law of universal gravitation. So on the first time that we talked about this, one of the things that we did is we set our gravitational force equal to our centripetal force. And let's do that again really fast and see if it makes any sense to us. We know that the centripetal force, let's say on a planet around the sun, if that's equal to the gravitational force, I end up with mv squared over r is equal to g big M little m over r squared, where little m is the mass of the planet, big M is the mass of the sun, and r is the effective orbital radius. We simplify this, we end up with v squared is equal to g m over r. I'm going to switch to a capital R so I'm being consistent here. But you're in circular motion, so what's your speed? Since you're in circular motion, your speed is 2 pi r over t. I'm going to square this whole thing. Okay, these r's are the same, so I end up with 4 pi squared r squared divided by t squared is equal to g m over r. And now all of a sudden we have the same, we're looking at something really interesting. If I multiply both sides by r and divide by 4 pi squared, I end up with r cubed over t squared is equal to gm all over 4 pi squared. And so this idea here that r cubed over t squared is a constant because the universal gravitational constant is constant, force constant, pi is constant, and in this case this is the mass of the sun and it doesn't change. And so we can see that this is consistent. This was Kepler's idea, this was Newton's idea, and we can see that although they're contemporaries, they came up with similar ideas, they kind of verified each other. One last idea I want to take into consideration here is the idea that we talked about that the orbits aren't really circles, and so this idea of the R is not exactly true because they're not going in circles, they don't have a radius. They're ellipses, and so how do we compare the R for a circle to something in an ellipse that still makes some sense? Well, it normally manifests like this. So if we take our ellipse here, well, that's not a great one, but we'll go with it. We take our ellipse here. We know that the planet is going around the sun, or in this case, that's much more of a comet. Planets don't look like that, they're almost circular, but it doesn't matter. Here's the sun at one of the focal points. People always ask, what's at the other focal point? And the answer is nothing. Like, is it a black hole? No, it's nothing. But an ellipse still has some symmetry. Mine doesn't, but ellipses do. If you look, there are axes here. Okay, and we'll pretend this meets in the center. This distance here along this axis from here to here is called the major axis, and half of that is called the semi-major axis. And we use the little letter A to represent the semi-major axis. And so, instead of using R here, we use little a. And so it's a cubed over t squared is equal to g m over 4 pi squared. And if we're talking about the solar system, this would be the sun. This is true for, let's say, the objects orbiting the Earth. The a cubed over t squared ratio is the same for all of them. It would be different than for the planets because the mass of the central body is different. So semi-major axis, that's that. Since we're talking about orbits of comets and stuff, let's revisit the energy concept real quick and talk about the potential, gravitational potential and kinetic energy of these things. Because it's really interesting the way that it manifests. One of the things that we know is that the total mechanical energy is equal to the kinetic energy plus the gravitational potential energy. I told you yesterday that the gravitational potential energy can be expressed as negative Gmm over r, where this is the mass of the central body, this is the mass of the orbiting body, this is the radius of the orbit. We know that the kinetic energy is equal to 1/2 mv squared, where this is the mass of the orbiting body and this is the orbiting body's linear speed at that moment. But watch what happens if we go back to that same construct that we started with. If we set the centripetal force equal to the gravitational force for an orbiting body, we end up with mv squared over r is equal to g big M little m all over r squared. Now if we let one of these r's go, we cancel them or magically disappear, we end up with an expression that looks like this. mv squared is equal to g m over r. Now these look very familiar, so let me come up here and let me rewrite this. I have this mv squared on the left side is equal to g big M little m all over r. So this looks very similar to this gravitation equation, except for this one's positive, this one's negative. And this looks like 1/2 mv squared, except for you need a half. So what we're going to do here is we're going to divide both sides by 2, or put a half out in front. And we end up with 1/2 mv squared is equal to 1/2 g mm over r. This left side is the kinetic energy. This right side is 1/2. Basically, this thing here is the opposite, the negative of that. So it's 1/2 of negative u. So we're saying that the kinetic energy of an orbiting body is equal to -1/2 of the gravitational potential energy. That's a weird idea. It's even weirder if I take this and I'm going to now plug it into this E total equation here. So if I do that, let's change colors. If I plug it into this E total here, I'm going to substitute in right here for this K. This is negative UG over 2 plus UG. Well, this is a full U, this is -1/2, and so if I add those together, the total mechanical energy is equal to half the gravitational potential energy, which is crazy to me. It's crazy to me. And so this would be negative GMM over 2R. And then, if we realize that these things aren't really going in circles and they don't really have radii, then we can say that just like we did earlier, instead of using R, we're going to use the semi-major axis, which is 2A.